Hello and welcome to the webinar. We're still seeing a lot of attendees joining in, so we'll wait a couple of minutes and let some more people join. We're at about 200 now, but since we've got quite a few registrations, we'll just give a couple of minutes. Okay, we're at 2 minutes past, and we're at about 250 people in. So let's start off and do some introductions while we wait for a few more people to join in. Um, I'll share my screen, and we can then start. Let me know when you if you can see it now.
Yes, yes, we can see it now.
Great. Right. Is that good?
Yes,
Perfect. Okay, so I'll just introduce myself first. I'm Shilpi, and I'm your host and moderator for the day. I head publication support services at Cactus Communications. I trained as a dentist during my bachelor's and then majored in epidemiology and biostatistics during my master's program at Boston University School of Public Health and the Free University of Amsterdam. Before joining Cactus, I worked at the National Health Service, the NHS, in London, and at Imperial College London for about 10 years, managing research delivery and auditing public health programs. In my current role at Cactus, we're constantly looking for new ways to support researchers and authors in their research and publication journey by offering services such as pre submission peer review, journal selection, and journal submission. I'll tell you a little bit about Cactus itself. Cactus Communications is a global scholarly communications company, and we've been around for 20 years. We have a presence in several locations across the globe, and we work with researchers through our brands, including Editage, Impact Science, Cactus Life Sciences, Cactus Labs, Unsilo, and Researcher.life. At Editage, we focus on supporting researchers with various aspects of their academic journeys, be it publication, post publication, research communication, providing resources to help them navigate the publication process, and several other aspects. Our newest service offering is a full suite of statistical support services, including simple and complex statistical analysis, a critical review of your stats work with suggestions on how to make it more robust, as well as support with systematic reviews. There's also an introductory discount of 20% on all stats services at present. So you can head over to our website, editage.com, to find out more details. Now, coming to the topic of today's webinar. Most research needs statistics. For example, picking an adequately sized sample or determining the most appropriate tests to answer your research question. It's crucial to use stats correctly to make your research more robust and easier to publish. However, most researchers never get the opportunity to learn how to do this properly. So, to help us think through some of the statistical and research design problems to avoid in manuscripts, we have today with us a very impressive panel. Dr. Regina Nuzzo, PhD, is from Gallaudet University and will talk about good study design. Regina is a senior advisor for statistics communication at the American Statistical Association and an award winning science journalist. Welcome, Regina. Dr. Kristen Sainani is from Stanford University and will speak about common statistical problems and how to avoid them. She was the recipient of the 2018 Biosciences Award for Excellence in Graduate Teaching at Stanford University. It's lovely to have you with us today, Kristen. And finally, Dr. Joe Røislien is a mathematician, biostatistician, and professor of medical statistics at the University of Stavanger. He will share his thoughts on statistical and research design problems. He developed and hosted the popular science show Cipher or Digits on NRK and was the first ever Norwegian to be a host on Discovery Channel. So this is really exciting, Joe. Don't miss the Q&A round after the talk where the panel will address your queries. Also, after the webinar ends, we have an expert biostatistician with whom you can talk about your stats problems and ask questions. So all of that towards the end of the webinar. But for now, over to you, Regina.
Wonderful. Thank you so much. Let me see if I can share my screen. Get that. All right. Hopefully you're able to see that. Someone speak up. If not.
Yes, we can.
Thank you. Wonderful. Thank you. Thank you so much for the invitation to speak here. I'm going to be talking about research design, 2 common problems, why they matter so much and what to do instead. I'm a professor of mathematics teaching statistics at Gallaudet University in Washington, D.C., and also a lecturer at Stanford University. Now, research design is huge, and there are lots of different types of research design. Obviously, we can't cover them all in this, so I'm going to be talking about 2 problems that are common in all research designs, and that's inadequate sample size and non-representative samples. And I'm going to illustrate both of those with some real examples of published studies in the literature. The first one, starting with 2008 in the Journal of Personality and Social Psychology, very interesting little study about romantic red. And they found that women wearing red or against a red backdrop or somehow having red around them relative to other colors led men, heterosexual men, to view those women as more attractive. So this is definitely research you can use. Yes, this is something in, social psychology, but the ideas I'm talking about apply generally. Now, there were a lot of different experiments within this study. I'm going to talk about one of them. They asked a group of college men, imagine that you're going on a date with this person, showed them a picture, and you have $100 in your wallet. How much money would you be likely to spend on your date? And the men were randomized into one of 2 groups. One group saw this woman down at the bottom wearing a blue shirt, and the other group was randomly assigned to see the exact same woman, except now she was wearing a red shirt. And of course, they wanted to see what the difference was on how much men were willing to spend on dinner with this woman and the difference between these 2 groups. And this is what they found in this particular experiment, that on average, the men who were seeing the woman wearing red were willing to spend about $58, and the men that were seeing the woman in blue were only willing to spend about $32. So that's a difference of $26, which is a huge difference. That's like lobster dinner, steak dinner, and getting dessert and a bottle of wine and not. So what was going on here? Sample size of 12 and 11. Now, this is really small. And what I wanted, a sample size of 23, what happens when you have a sample size of 23? So I decided to, one of the nice things about being a statistician is that you can simulate these things. So I asked the question, what would it look like if I did repeated studies with size 23 in a universe where I decided the true difference on how much men were willing to spend on a date for a woman wearing red versus blue was only $5, because I felt like $26, that might have been a lot. And I wanted to see what was if the real effect was $5, and I took samples of size 23. So I created this simulation. And what do you see going on here? So blue is better, is on the left, red is better, is on the right. And you can see this little ball. Each of these balls, then those points represent one study, and I simulated 1,000 studies, so you can see this, the simulation going on over time, and you can see how much it's bouncing around. So you have this dotted line in the center. This is where the true difference is only $5. So I set this up. This is the nice thing about being a statistician. You can say, okay, what would it look like if this were true? Then this dashed line that you see on the right is that $26 difference that was found in that 2008 study that I was talking about. And this is the difference. So further to the right means red was better, further to the left is blue is better. And when you're looking at this, you can see that it really does bounce around a lot. So if the true difference is even only $5, you're seeing sometimes studies that will show up with a difference of at least $26. Sometimes you're seeing, $30 or $35. Sometimes you're also seeing the other direction where blue is better. Now, this is really jumping around a lot. Then I said, what would it look like if I did repeated studies with N of only 200 in that same universe where the true difference of wearing red versus blue was only $5? And this is what this looks like. So again, same setup, but what are you seeing here? The difference, that bouncing around from study to study, is much smaller. Sure, sometimes you're still finding out that blue is better, that men actually prefer a woman wearing blue, some is red, but you're seeing much less wild swings. And so you can have these side by side. N of 23 on the left, N of 200 on the right. This is if you had actually taken a big sample size on the right. And you can see that on the left, you're going to end up with bizarre swings that are way outside of what reality actually is. If you're taking a big sample size on the right, you're much closer to reality. So this suggests that if we were to take a big sample size, we might not actually be able to replicate this big finding of $26 difference. So this is the important thing I want you to remember. With small sample sizes, your results are more likely to be inaccurately big or inaccurately small, or even in the wrong direction. So this is the problem with a sample size of 23, something small, is that when people try to do a replication, like this group did a few years later, about 10 years later, now they did it with a sample size of 242 instead of 23. And what do they find now? A very weak effect. That's exactly what happened, because this 23 is misleading. They found a very weak effect actually in the opposite direction, finding that actually men didn't prefer red. They preferred other colors. So the bottom line here is don't really prioritize getting a sample size that is big enough. And how can you do that? Plan your sample size before you start collecting data. Don't just keep on collecting data until you feel like you're done or you've gotten enough people. Work with a statistical consultant, a biostatistical consultant, and or use power calculation software such as G-Star Power, which is this wonderful free software that will help you figure out what your sample size needs to be for your particular situation. And statistical power is this idea that we're talking about here. It's the chance that you will be able to spot any real significant effect with your given sample size. And I believe Kristen and Joe will be talking more about that. This is just an example of what the software will tell you. It will say, I put in some things here. It said you actually need a sample size of 260. And if the researchers had done this, they wouldn't have just stopped with a sample size of 23, and they would have had a much more accurate result. So you put in all the information you need there, and it pops out with the answer, which is really wonderful. All right, example number 2, a non-representative sample. So sample sizes, big, are good, but is it always the most important thing? So let's time travel back to May 2021. The big question on everyone's mind is how many people have gotten the COVID-19 vaccine? This is when they were worried about enough uptake globally. There were 3 different groups that were doing ongoing surveys of the general population. One was Delphi Facebook. This was through Facebook. They had about 250,000 responses per week, and they estimated about 70% of people in the US in May 2021 had gotten the COVID-19 vaccine. There was another group, Household Pulse. This was through the US Census Bureau. They had 75,000 responses every 2 weeks. So this is huge, 250,000, 75,000. They estimated about 67%. Then there was this other odd little group, Axios Ipsos. It was a media outlet and polling firm partnership. They only had 1,000 responses per week, which is still a lot, but not compared to 250,000 responses per week. And they had a much lower estimate. They have 57%. So the nice thing about this is that we are able to see exactly what the answer is. We can also see what the response rate was. So response rate of only 1%, 7%. This Axios Ipsos on the right, they had a response rate of 50%. So that's looking a little bit better, but they still had this small sample size. And I just told you small sample sizes are bad. We want big sample sizes. You can also look at who each of these groups was reaching. So Delphi Facebook was reaching Facebook users. And people were responding through their Facebook feed. This US Census Bureau, they were working from this master list of all the addresses with known contact information from the Census Bureau that covered the entire US. This one on the right that I'm kind of viewing with a skeptical eye, they were participants in what's known as a knowledge panel or an ongoing panel. They were invited participants, but it wasn't just a random sample. These were people who had already agreed to work with this firm and answer survey questions over and over. They already had a relationship, so it's a very different situation as what was going on with the other two. So as I said, the nice thing about this is we can actually look at what the truth was, because the Centers for Disease Control in the US was able to pull together all the information months later about what the true vaccination rate was. The thing is, we wanted the surveys at the time so we could see in real time what was going on. But here we can have that ground truth coming back. And what's happening here? We found that the true vaccination rate from the CDC administrative records was only 53%. So most people, everyone overestimated. So Facebook, which had this 250,000 responses per week, they had a 17 percentage point overestimate. This one that was working through the US Census Bureau had a 14 percentage point overestimate. But Axios Ipsos, which was dealing with this just, really small group, this really small sample size, they only had a 4 percentage point overestimate. So what was going on here? They were including other information. This Axios Ipsos was including other information in there, primarily about education. So Delphi Facebook missed the true educational distribution in the US because they were getting people off of Facebook, and they were oversampling. They were getting more overeducated people. The same thing with the Census Bureau. They were reaching more overeducated people. This Axios Ipsos, because they had this ongoing relationship, they were able to get people that were closer to the true educational distribution in the US. And this was the key. So I just said, hey, small sample sizes, not as good as bigger sample sizes, except there's this idea of big data paradox. And that's the bigger the data, the surer we fool ourselves when we fail to account for bias in data collection and participant selection. So that is the flip side of what we're talking about here. Yes, bigger sample sizes are better, but not as important as getting a sample that is truly representative of who you want to make conclusions about. So how do you do that? My advice, carefully define your target population. If you want to talk about the whole population of undergraduates in the US, or the whole population of, patients or particular people with a particular type of disease, that's good. Know exactly who that is. Know exactly what the age range is and educational distribution. Then plan your study recruitment strategy carefully. Ask, who from my population is not being included in when I'm designing this research design? Who is likely not to participate? How does my sample differ from the target population? How can I reach the participants that I want to reach? So sit down again before the study very carefully and think about these questions, how you're going to answer them. So sample size is important, but having a representative sample is even more important. So thank you, and I look forward to talking more with you later. Thanks.
Thanks so much, Regina. That was absolutely fascinating. I think both of the case studies which you discussed was so pertinent, and you start to think, oh, this is exactly how it should be. We should get as big, and the bigger sample size is such a almost a cliche where you think that the bigger it is. And so the second one was really useful. Fantastic. All right. So with that, we'll move on to Kristen.
Fun. Let me just share my screen here.
Yes, please.
All right, I'm going to be talking about the stats side of things. So after you actually have data, hopefully everybody can see that okay.
Yes.
And yeah, good. Yeah, like Regina, I'm going to talk about just two errors just for, there's many errors we could talk about, but two of my favorite because we have limited time here. So I'm going to talk about simple math and data errors. I spend a lot of time reviewing papers, and majority of the errors I find are nothing too fancy. They're just simple math and data errors. And then I'm also going to talk about clinically irrelevant effect sizes. So simple math errors are surprisingly common. I review lots of papers where there are just things that the sample sizes don't add up. There's simple calculation errors or math that doesn't make sense. I sometimes see data in different tables or figures that's supposed to be the same data set, but they don't match, right? So this is all a tip-off that there's some sloppy data handling going on, or people are just not being careful or not thinking about what their results mean. So I'm going to use an example from the published literature. It'll take me a little bit to explain what you're looking at here, but we're going to talk about an error in this particular paper. So this figure comes from a meta-analysis, actually one of the most highly cited meta-analyses in strength and conditioning research. I do a lot of work over in sports medicine and sports science. So what you're looking at here is a scatter plot, and you should understand that each of those dots, because it's a meta-analysis, each of those dots represents a group of athletes rather than a single individual. So this was a meta-analysis. Specifically, that meta-analysis means you're going to the literature and you're pulling out data from already published papers. So the authors of this meta-analysis were interested in looking at the relationship between improving the strength in your legs and improving your ability to sprint quickly. So all of the underlying studies in this meta-analysis involved athletes who had undergone some kind of training intervention, 8 to 12 weeks long. And before the intervention, all of the athletes had had their squatting ability or their leg strength measured. And then they had that measured again after, so we could see the improvement in their squatting ability. And they had their sprinting ability also measured before and after, so we could see the improvement in their sprinting ability. So on the x-axis here, you're seeing the sprint effect size. That represents the improvement in sprinting. And for sprinting, negative numbers are good because you want to get faster. On the y-axis, you're seeing the improvements in squatting ability. This is how much weight you can squat. For that, higher numbers are good because you want to get stronger. And they've calculated here the correlation coefficient. So this is a scatter plot, and they've superimposed this as a linear regression line. They've calculated the Pearson's correlation coefficient, telling us something about the relationship between the improvement in squatting ability and the improvement in sprinting ability. So for those of you who are familiar with Pearson's correlation coefficients, they run from -1 to +1. -1 would mean a perfect inverse correlation. And here, because we want sprinting to get faster, so more negative, we are seeing an inverse relationship. The size of that correlation coefficient is huge. That's -0.77. That would be considered a very strong correlation between these two things. So the authors concluded that the meta-analysis suggests that there is a transfer of lower body strength training to sprint performance as indicated by the very large correlation between squatting strength effect size, again, the improvement in squatting, and the improvement in sprinting. And they cite that correlation coefficient. However, there's a reason I'm showing you this example, and you might have noticed it if you're kind of staring at this figure. You might have noticed that up in the left-hand corner, there is what you might call a rogue data point or an outlier. And so when you see a data point like that, you should start to think carefully about, well, why is that data point so different from all of the other data points in this figure, right? Everybody else is down here, and then we have this one way up in the left upper hand corner. it should make you worried about maybe it's possible there's an error. It also could just be a really weird study, but you'd want to consider how much influence is that study having on your effect, because you can see what's happening here is that data point off to the left is kind of pulling that linear regression line towards it. It's actually inflating the correlation coefficient that you see here. So actually some authors who are in strength and conditioning research had come across this paper and sent this figure to me and said, hey, what's up with that data point? So what we then did was to say, well, okay, what does that data point actually mean? I've told you that the x-axis has something to do with your improvement in sprinting. The y-axis has something to do with your improvement in squatting, but I never told you what are the actual values? What do those numbers on the x and y-axis mean? So what those numbers are actually, these are standardized effect sizes. And we typically calculate these kinds of standardized effect sizes when we are doing a meta-analysis. So what they did was they took, remember, each dot is a group of athletes. They took the athlete's squatting ability, how much weight on average they could squat after the intervention, post-intervention, and they subtracted the mean before the intervention. And that gives you the difference in, say, units of kilograms or units of seconds. But then we divide that by the standard deviation in the squatting ability or the sprinting ability to get this standardized effect size. What that means is that the units for the x and y axis are actually standard deviation units. And so if we think about the coordinates of that rogue data point, what we're actually seeing here is that that rogue data point has an x coordinate of about -5. That would mean that these athletes, on average in that study, improve their sprinting ability by about 5 standard deviations. And the athletes, you can see that on the y-axis, the coordinate is close to 15. So that would mean that the athletes in that study improved their squatting ability by about 15 standard deviations. And so now I'm going to have you guys take a little poll to ask you, what do you think of that number, the 15 standard deviations improvement? Is that large? Is that small? Like, what does that mean? So think a minute about what a standard deviation unit means. And so if we could have the poll come up now and have everybody attempt the poll. And I can't actually see the poll over here, so I won't know when when the poll is done.
Kristen, I can tell you a little bit about it. So
Okay, yeah,
it's seeming like about 45% people feel like it's an implausibly large effect. About 17% are saying very large, 20% large, and only about 9% are saying that it would be a small effect.
Excellent. Okay, so you guys are actually doing better than most places where I present this, because it's hard if you don't deal in standard deviation units normally to understand what that means. But yes, this is an implausibly large effect size. If you think about how big a standard deviation is, a standard deviation represents sort of roughly the average distance from the mean. So if people on average are 1 or 2 standard, most people are within 1 or 2 standard deviations of the mean. If you think of, for example, a normal curve, what would it mean to take a whole group of athletes and have them improve by 15 standard deviations? That is so large that it just can't be true. So I actually went to that underlying paper when I saw that 15 standard deviation improvement and said, hey, let's pull that underlying paper and actually look at what that would mean if I translate it back into kilograms, the amount you can squat in kilograms. So it turns out that in that underlying paper, for that group of athletes, the baseline mean squatting ability was 123 kilograms with a standard deviation of 8 kilograms. So now I can just do some simple math. What would a 15 standard deviation improvement actually mean there? Well, 15 times 8, that's going to add 120 kilograms. So all of a sudden, that would mean that on average, not one athlete, but all the athletes on average had improved their squatting ability from 123 kilograms to 243 kilograms. That is not physiologically possible over an 8-week training. I don't care what steroids you put those athletes on. That is not a plausible improvement. So this is telling us that this has got to be an error. And in fact, this was an error that the authors of the meta-analysis had made when they were calculating their standardized effect sizes. So what went wrong here is that the authors confused standard error and standard deviation. And this is a very common confusion. Those things sound alike, standard error, standard deviation, but they are not the same. The standard deviation tells us about the variability in the squatting ability of those athletes. The standard error tells us something about the variability of the statistics. So it's a totally different quantity, and you need to use standard deviation when you're calculating a standardized effect size. And we can actually, I pulled out the numbers, was able to recreate that. If you take the standard error and plug it into that formula I showed you, you do indeed get an effect size of about 15 standard deviations improvement. If you correctly plug in the standard deviation, you still get a very large effect size, but now it's at least plausible. It's an improvement of about 3 standard deviations. Of course, that error got through like all the authors of that paper, the editors of the journal, peer review, right? So how did that get through without anybody noticing that there's this wildly different data point that makes no sense, right, when it's sitting there on the graph? Now, it turns out this led the researchers who sent this to me, once we saw this error, we started digging into other meta-analyses to say, hey, how often does this error occur? And it turns out that we were able to find lots of papers, lots of meta-analyses in strength and conditioning research that were highly cited papers but had the same error. And it doesn't take a degree in statistics. So if you look on the left-hand side here of the screen, this is a forest plot, which is another way that you see data presented in meta-analyses. There's 2 errors there. I bet you can all pick out the errors. The black ones are the individual studies. So there's 2 of the black boxes there that are not like the others. So those 2 that you can see that are the 7 and 5 effect sizes, those are both, we were able to verify that those indeed same error. They put standard error rather than standard deviation. And we saw this all over the place. Different study, same error. You can pick them out again pretty easily. It's the 2 that don't look like the others. So how do these things occur though? How do these kinds of like silly math errors get through peer review? How do they get through journal editors? It's because people aren't paying attention and aren't thinking carefully about numbers. My theory is that a lot of people are so intimidated by statistics that they kind of like don't, they check their common sense at the door. So you always want to use common sense. To avoid these kinds of errors in your own work, it's important that you check and understand your data, really understand what's going on in your data. So as a statistician, 90% of what I do is really processing data and checking and understanding data. You want to keep an accurate record in code. You actually do want to use code so there is an exact record of all the things that you've done on the data, so it's very easy to trace back on error. Pay attention to simple numbers. Just use common sense. Ask the question, do these numbers even make sense? And then draw lots of pictures. The authors of that meta-analysis had drawn a nice picture. And actually, if you were paying attention and looking at that picture, you might have been able to pick out that data point didn't make sense. All right, second problem, another common problem, just people get overly bogged down in p-values. So you have to understand that a p-value is useful in some contexts and not useful in other contexts. We don't always need a p-value. It doesn't always have meaning. In particular, if you have huge sample sizes, you can have such extreme statistical power, such extreme precision that you can detect very small differences between groups that will be statistically significant but not clinically meaningful. And one of my favorite examples of this was a study that was published in JAMA a number of years back. JAMA, of course, is one of the top medical journals. And they had a huge study. They followed 34,000 women for about 13 years. So it was a tremendous data collection, really wonderful study. They just got the punchline wrong because their main claim and the headlines that were picked up by the media were, they said, hey, we found that the women who exercised the most, about an hour a day, gained significantly less weight than those who exercised the least. And it was highly significant. The P was less than 0.001, got a lot of attention in the media. Now, there was indeed a significant difference between those 2 groups, the high exercise and the low exercise group. So now I'm going to have you take a little poll and see if you can guess how much less weight did that very high exercise group gain compared with that very low exercise group. See if you can take that poll and make a good guess. And again, I can't see the poll, so when it's ready, if somebody could fill me in on the results, that'd be great.
Yes, I'll do that for you, Kristen, in a minute.
Thank you.
They're just starting to come in now.
Perfect.
Okay, this time it's more evenly distributed between the 3, 1, and 0.5 pounds.
Okay.
There's about 13% who are saying 0.1 and about 13% saying 5, but the rest are around the 25% for the 3, 1, and 0.5.
Okay. Yeah. So you might expect that, like, hey, this is a significant result. We're going to see something that's actually meaningful. The actual answer is 0.1 pounds. So the women who exercise the most gain on average 0.1 pounds less per year than the women who exercise the least, which is a surprisingly small amount. But if you go to the tables, you just check in the tables. I'm going to zoom in here. That's actually what I'm going to translate now for you. This is a 0.15 kilograms. Those who exercise the least gain 0.15 kilograms more than those who exercise the most. But that was over 3 years, because they did this. They measured the women every 3 years. So that translates to about 1/10 of a pound per year. The entire confidence interval here, if you look at the whole confidence interval, everything in that confidence interval is really, really small. So it's highly statistically significant. How can 1/10 of a pound per year trigger a significant effect? It can do that simply because the sample size here was so huge. But this is a classic example, the statistically significant effect that's not clinically significant. And the best part of this study is that they actually had a picture in figure 1 of their paper, that if you look at the figure, they're looking at the high, medium, and low exercise groups over time. Time is on the x-axis, weight is on the y-axis. And what's really interesting is, yes, that high exercise group indeed was lighter to begin with. But the whole point of the study was to follow the women over time and see the trajectory of weight gain. And those lines are just pretty parallel. So really, there was no meaningful difference in weight gain over time. So how to avoid this error? You always want to pay attention not just to the p-values, but also to the effect sizes. And again, use common sense, plot your data. They did have a nice plot in this paper, but unfortunately the authors looked at that and came up with a convoluted explanation for why that plot wasn't the answer. So in general, principles of effective data analysis: check and understand your data, keep an accurate record and code, pay attention to simple numbers, use common sense, draw lots of pictures, and pay attention to effect sizes. And I have lots of online resources for training in both statistics and writing. I'll put those resources up here now, but you can find those just by Googling me.
Fantastic. Thank you so much, Kristen. That is, it was so so brilliant. The thing about p-values and going by just looking at them, and then you think that, oh, this is the beginning and the end of everything. It was fantastic looking at those cases, and I'm sure that that's going to be so useful. We've got so much of appreciation coming in from the audience about it. Thank you so much. Joe, we move to you now. Thank you.
Thanks. It's my turn to do the share screen exercise. I'll try to do this. Here we go.
Yes.
So you can see it now, right? Excellent. Thank you.
Perfect.
Yeah, so my name is Joe. I'm a professor of medical statistics. I've been a statistical collaborator of hundreds of research projects within medicine and health sciences. So I get asked questions like this a lot about statistical problems, research design problems in manuscripts. And the questions will typically be like this. I mean, people send me like the methods section of their paper, and hey, can you read through the methods section, see whether it looks okay? Or they send me stuff and call me up and say, hey, my supervisor said I should use a case control study design. What do you think about that? Or they ask me questions like, how do I perform a logistic regression in SPSS? So being a statistician, these are the types of questions people will ask me, because I know methodology and they know I know methodology. So this is what they want me to answer. And I answer these questions, but I tend to answer differently. People have an idea that statistics and research methodology is kind of detached from the research project itself. So when people ask me questions about research methodology, I tend to give a bit of a broader answer. So I tend to say, Okay, so a research paper, what does it look like? A research paper consists of, depending on your field of science, basically there are still 4 parts. You have an introduction to the problem. You describe the methods you've used. You present the results, and you discuss the whole thing. That's basically what we're doing. And there are some really key things here that you need to remember in order to answer questions about methodology. Now, the introduction will usually consist of 3 parts. You say something about the research field that you want to present, and then you zoom in on what's missing. And then you say that I want to target this. And then you post like a research question where you say what you want to do in this research paper. That's basically what you're doing. The broader view, the state of the art, what's missing, this is what I'm going to do. And this is key. The research question is key because the research question defines everything else in the paper. Now, the research question, if you have a question, you will have to answer that question. How are you going to answer the question? That's the method section. That's the design. That's the statistical analysis. So basically what that means is that your design, your methodology, your statistical analysis is defined one-to-one by the research question. And then you have an answer to that question. And then you discuss that question. I mean, how was your findings? Did they fit with other research within the field? Why did they fit? Why did it not fit? And then you sort of zoom back into the introduction. And this here is why the method section is the most important section of the whole paper, right? Because if your design and your statistical analysis does not hold, it means your results are worthless and your discussion and conclusion meaningless. And what defines the method section? Well, it's defined by the research question. So when people ask me questions like, can you read through the method section? My supervisor said I should use a case control study design. How do you perform a logistic regression? My answer will always be, so what's the research question? What's the research question? What's the research question? I always come back to that single question because that will define everything else. So the whole idea of just presenting someone like us, statisticians, methodology experts, with a method section and read through it kind of doesn't really make any sense. And it's funny, as a statistician, I mean, I've read all the stats book. They're hard. They're a struggle. There are names of methodologies, names of old dead white guys, mostly from the UK in the early 20th century. And you have to remember all of that. It seems like a buffet, right? Where you can pick and choose various statistical methods. But statistical analysis and research design is nothing like a buffet. You can't go around and pick and choose whatever you like. Because what you're picking, what you have to choose, is defined by the research question. And every year we have, in several of the master programs that I teach, or I'm one of the teachers, we have classes where people will present papers and we will sort of dig through them and see what it looks like. And we have classes where people will present their master thesis projects and we go through it and see what it looks like, whether it seems feasible. And a couple of years ago, we had this student, and what she wanted to do, she was working in pre-hospital critical care, and she wanted to study the use of pre-hospital critical care system services in some sub-Saharan country. And then she presented her project and she was like, I want to do some qualitative stuff. And we're like, that's not the way it goes, right? You cannot decide on your methodology before we know what the question is. And then she sort of proposed her question and use of pre-hospital critical care services in sub-Saharan countries. And she was like, so I want to do some qualitative stuff, and I want to send out this questionnaire. And we were like, but in a questionnaire, you have already defined the questions. You have defined what people can actually answer. So you have categories, which means you will get counts and numbers, which really sounds like statistics. So, and she was like, yeah, but I don't like statistics that much. I'm afraid I might do it wrongly. So I want to do qualitative stuff. So what if I just send out a questionnaire that has like these huge boxes where people can write whatever they want? And we're like, what? It sounds like you should talk to someone rather than just collecting text. But her aversion against quantitative analysis and statistics was so deep that she struggled to move on. But the problem is, you sort of have to learn the methodology that is related to the type of questions you ask. If you tend to ask questions that will result in numbers, that will mean statistics. You have to learn statistics. If you ask questions that result in people's emotions, subjective opinions, well, then you can resolve it with text. And I'm saying this because the neat thing about numbers, the reason why I love statistics and have questions that can be resolved by numbers, is the fact that it's almost purely defined one-to-one what to do about it. So I'm very briefly now going to present to you a full basic class in statistics on one single slide, right? The good thing about statistics is that it's maths, and maths is right or wrong, which means that as long as you have a research question, you get your data, there's one thing you can do about it that's right, and the rest will probably be wrong. I'll do this very briefly. So you have two main types of numbers. You have numbers that are categorical. That means you have categories that you can count, like biological sex, hair color, car brand, things like that. Boxes, and you count how many is in each box. Or you have something continuous that you've measured, right? Your height, your salary, your blood pressure, something like that. Those are the two main types of data you have in quantitative studies. And when you know what type of data you have, what you have to do about it is already basically given, right? If you want to summarize a categorical variable, you have to count them. You can calculate fractions or percentages. That's it. If you want to summarize continuous variables, you do mean if the data is symmetric, or you do median if they're skewed, basically because the mean will be sort of pulled upwards by extreme values. So you have to have something, some alternative, and then you need a number for the variation as well. So that's how you summarize it. If you want to find the association between two variables, called bivariate analysis, if they're both categorical, you will have a 2x2 table. And you do chi-square tests. If they're both continuous, then you will have a scatter plots, and you do correlation. If one is continuous and the other categorical, then you will have box plots, and you do t-tests and Mann-Whitney tests, or ANOVA, depending on whether it's symmetric or not. And the names of all these tests, that's what's in those books, right? And this is what, if you have an experiment, if you have the real world, you have the observational data, you need to adjust for confounders from the real world. And then you do logistic regression if you have a binary outcome, and linear regression if you have a continuous outcome. So this is Statistics 101 on one slide. So finding the right statistical method really isn't that hard if you know what data you have and you just do what it has to be done. And the reason why I'm saying this is because when I get questions like these, statistical and research design problems to avoid in manuscripts, I review a lot of manuscripts. I have read and participated in hundreds of research papers. And the thing that I look for is, does it make sense? Does the whole thing make sense, right? So you have a research question, and the question will define what you should do to answer that question. If you want to compare two different pills, well, then you have to create two groups, and one group will get pill A and one group will get pill B, and then you see what happens to them. If you want to see what happens if you introduce a new policy in the healthcare system, well, there's something that happens before policy change, something happens after. Then you have a temporal measurement of something, time passes, there's a change at some certain point, and you move on further. So this is a temporal question. So the stats will sort of give itself. which means that the words that you're using, that's my main point here. I'm looking for, do you know what you're doing? Have you understood what you're actually doing here? Because the question defines the design, and the design will give you a specific type of statistics and numbers. The numbers, you will have to do something about it in a particular way. And it's really fun to see people who are not sure of what they're doing, who are looking for a quick fix. And you read through their manuscripts, and the method section with the design and the statistical methods, words are just scattered everywhere. You're just trying to use as many words as you can just to cover in, and hopefully you've done the right thing. So you call your study a multi-center randomized feasibility before-after crossover design study. What on earth is that? It's just everything, right? If you know exactly what it is, then the design should be fairly brief. And then you get the data. And what type of analysis have you done? Well, they'll say, we did chi-square tests for categorical data, with t-tests, Mann-Whitney tests, logistic regression, with just for confounders in a mixed model. And then we tested for this and that and did to see whether it mattered. You just tried everything. And that makes me really, really uncertain when I read manuscripts like that. Do they know what they're doing? Or are they just trying everything and hopefully they will have said the right words so it will pass peer review? What I'm looking for is people who hits the bullseye, right? Your design is fairly brief. This is what we did. And then the statistical analysis that we used was this, because it matches the design. And the results can be interpreted like this because it matches what we did. The words you use to describe your methodology, your design, your statistics will kind of reveal whether you've understood what you're doing or not. And understanding is basically what we're looking for, to sort of remove all those mistakes that we've seen before that the two other professors have talked about. I mean, do you know what you're doing? Have you thought about everything? So what I usually advise people when they're writing up their manuscripts is trying to help me as a reader, safeguard me and make sure that I can trust that you've done the right thing, right? That you understand what you've been doing. So the research question, state it very, very clearly. Let there be no mistake what you're trying to figure out. Because then it will be much easier to present the design properly, and don't just say what you did. Make me understand that you know why you did it. Tell me briefly why this design is appropriate for answering the research question, right? And if you know what your question is, the books will tell you what research design will fit. So let me know that you know. And then you did some statistics. Don't just tell me every statistical method you know. Pick out the ones you need and tell me why this is relevant for this research question and the design you've used. I mean, the method section, statistics section should be really, really brief if you know what you're doing, right? Clarity, clarity, clarity. That's what I'm looking for. So when people ask me questions as a statistician, what are design problems? What are statistical problems that we can use? Well, there really isn't a quick fix. But what I want is a firm, solid line through the whole thing. The methodology section is dead important. Defines what results you're going to get, and then defines what discussions you will have. So the method section is key, but then you need to know what you're doing. And if you're able to state the research question really clearly, and you struggle with the design and statistics, well, call a statistician. They will be able to help you out. And the first question they will ask you is, what are you actually trying to figure out? It will help you from there. Thank you.
Fantastic. Thanks so much, Joe. That was so useful. And I can completely see this sort of thing being such an issue, especially I think even the other way around, where there's a lot of data that you've got, and then you try and figure out research questions just because you've got the data, and then you're trying to work it backwards
Yeah.
to figure out what kind of research questions can I get out of this and what kind of stuff can I write. And then it's the same sort of catch-22 situation again. Brilliant. Thanks so much. That was so useful. Regina, Kristen, Joe, all of you, your everything that you've spoken to us today, I know that the audience has been very highly appreciative. There's loads of questions coming in, and I know that we're nearly getting to time, but I'll quickly go through some of the questions that have come in. So please feel free to speak up and answer as whoever feels appropriate for that. The first one's about sample size. What's the best way to arrive at a sample size when there are no prior studies at all on a particular prevalence? Regina, do you want to take that?
Sure, I can answer that one. I think this is an excellent question. This is something that researchers always struggle with. So it's going to be impossible to give, a perfect answer in this 2 minutes. So number one answer is consult your statistician. But a general point I want to make here is, yes, it's more difficult if you don't have previous information. But what I encourage you to do is look at what Kristen was just talking about. What is a clinically important difference in there? So it's not always based on previous information, because we saw from the first data I talked about, that might give you misleading information about what the real effect size is, and that's going to lead you astray. So what you should be doing is sitting down and thinking what is really important, what is useful if it's a clinical situation. You can also ask questions like, what is the cost for me for being wrong, for overlooking an effect? What's the cost for me for being imprecise? How precise do I need to be? But I'd encourage you to think about what is clinically important or practically important in there. So I don't know if Kristen or Joe has anything to add to that.
Yeah. Because I've been working a bit in pre-hospital care, which is a fairly young research field. So there's not that much information out there. So we struggle with this problem here a lot. And you go through research papers, you find nothing, and you're looking for the clinically interesting effect sizes, and you have a vague idea. But again, information is so limited that we don't know. So we have had to initiate a lot of pilot studies where you just go, okay, we don't know. So let's just collect some data, enough that will give us an answer to do the proper science afterwards. And the question is, how much information do you need? And in Norway, we have a huge problem with seasons, right? You have heavy winters, rain in fall, proper summer. So we tend to say we have to collect data for a full year, because there's no single time of year that will sort of represent the year. So we go like, okay, so we collect data for a year, and then we see what that gives us, and then we design the proper next study. So it feels sometimes it feels like a waste, because you just collect information to get the data you need to do the proper study. On the other hand, it feels rewarding because you see that, hey, we're the first ones to do this, which is actually quite cool.
Fantastic. Kristen, would you like to add anything to that?
That's it. They've covered it well. So I don't know if we have time for another question or not.
Yeah,
here,
there's one for you, which where the person's asked that since my area of study is in gymnastics and that doesn't have as many participants because there are not those many athletes, would you have any suggestions in conducting a quantitative research with a relatively small sample size?
Yeah, this comes up in sports science. I hear this all the time, right? Well, I can't get more than 5 participants. So there's several, strategies for getting around that. So one is sometimes it's okay to just do a descriptive study. We don't always have to do a study that calculates a p-value and looks for statistical significance. Descriptive studies are valuable. There's also strategies for increasing your sample size. Maybe, if you're do you always have to look at elite gymnasts, or can you look at a wider range of gymnasts? Can you pool data across multiple universities, multiple sites, right? Being collaborative. These are all strategies for increasing sample size.
Right. Joe, Regina, did you want to add anything?
No, but I would just
Okay.
want to say that the idea of doing multi-center studies is a thing that we often have to resolve to, basically because how do you increase numbers? Well, you need to get more people on board. The problem with multi-center studies is, it's a logistics nightmare, right?
And
But
funding
you
as
have to
well,
make
I
it
would
happen.
imagine. Yeah. Okay. I think we are out of time, but I just want to speak one more question, because there's a couple of people who've asked about not normally distributed data in a large normally distributed data set. So what path should I follow? Should it be parametric or non-parametric?
Yeah, it depends on the sample size. If the sample size is large, actually, the central, Regina mentioned central limit theorem kicks in, and actually that normality assumption is really not important for large, even moderate sample sizes, actually. So again, kind of knowing what you're doing or talking with the statistician can help. You'll see these things everybody worries about normality, and you think it's important for every case, and it's actually not.
Excellent. Okay, so what we'll do is we do have more questions, but we also have the opportunity for people from the audience to join a separate session in the social lounge after this webinar just finishes. We have an edited biostatistician there who may be able to help answer your questions. But we'll have to end this session now. It's been so great. Thank you so much, Regina, Kristen, and Joe, for being here today. I think that I've learned so much, and it's been so exciting listening to the things that you all have discussed and talking to all three of you. So I'm sure it's been hugely useful to our audience as well. Thank you very much. There's a feedback form for the audience. Please fill that in. The link should be available to you now. But that's it from us. Thank you all for joining us, and goodbye. Have a good day. Thank you.
Thanks, everyone. Great questions.
Thanks.